Suppose I have this circuit with a battery and an external resistance of maybe 6 ohms, and the battery itself has some internal resistance of about 3 ohms. And if I want to calculate the current, we can make use of, say, what we understand about voltage, EMF, and resistance and the Ohm's law to do that. Now, but what I like to do is to think of some ways to make such calculations easier, as well as to make drawing of this diagram easier. So it helps if we start using what we call circuit symbols to represent some of these components, rather than drawing a picture for each one every time. Okay, so what I could do is to let's see, I can represent the battery here using a circuit symbol which is written as 2 lines, a long line and a short line. Now the long line means a positive pole and the short line means a negative pole. Okay, so and then I can just draw some lines to represent wires coming out from the battery. Now there is this internal resistance of 3 ohms, and we could represent resistance with a rectangular box. So this is how it's normally shown, and then I can connect this to an external resistance. So that's my E, that is E, and that's my little r. I can connect this to an external resistance, which I can show as another rectangular box. That's my big R. So in this way, I have a schematic diagram which is easier to draw, and that is supposed to represent the same thing as this. And the next thing I like to do is this. I want to calculate the current. All right, let's say I want to calculate the current I, the conventional current, given the EMF, and the resistances. Now we can go through the Ohm's law and all that, but it's easier if we have a single formula for that purpose. And to do that, one thing that would be nice if we can somehow find what we'll call a combined resistance or an effective resistance to represent the overall resistance of this big R and little r. And what I mean is this. Now to make it easier to see, right, let me just draw this as another picture. Okay, so what I mean is this. Can I somehow find a resistor which I call maybe RC, maybe C stands for combined. Can I find a resistor so that when I connect the same battery to it, same EMF, I get the same current? Right? If I can somehow find a resistance that has the same effect as these two resistances separately, I can think of this as a combined resistance that can give the same current as these two resistances together. Now it would be nice if there's a simple formula that allows me to calculate this from when we know those two values. The reason is that if we can calculate a single resistance instead of having two resistances, then it's easy to use Ohm's law to just calculate the current directly. So let me first write down this meaning of the combined resistor of RC. So we call this a combined resistor is a resistor that gives the same current as the separate resistors together. So let's see how we can find this resistor. We need to make use of what we know, the equations we know that relates the resistance to the current and the voltages. So let's see. Now the voltage, right, for this resistance, to relate the resistance to the current, we need Ohm's law. We need V equals to IR. But the V here refers to the V across this resistor, which is the V2. So the V is the voltage between, say, two ends of the resistor. That's the V2. So that's V2. And for the small for the internal resistor, Ohm's law would be V equals to IR. In this case, V is the potential difference across little r, which I shall call, in fact, which I have called V1. Now there is another relation, if you recall from an earlier video, a relation between V1, V2 and E, because E is the work done to move 1 coulomb of charge all the way round the circuit, whereas V1 is the work done to move it through just this resistor and V2 through just this resistor. Now, no work is done along the copper wire. We're going to assume that it's so small that we can forget about the resistance in the copper wire compared to the R, big R and small r. So therefore E is just the total work done on 1 coulomb of charge, whereas V1 and V2 are the separate work done on the separate resistors. So this just means that the sum of V1 and V2 should be equal to E. So therefore, if I add these two, I should get E. Let's see. Let me write that out separately. The EMF must be equal to the separate V1 plus V2, since they're about the work done. And if I now add these two together, if I add these two, I will get E, and if I add those two, I will get I big R plus I little r. So that's the kind of relations that we can find for this circuit. Okay, so it's a little bit abstract at the moment. We are still not anywhere close to finding a combined resistor yet. But what I've done is I have used Ohm's law, and I've used the definitions of voltage and EMF to write down some relations, write down some equations. Hopefully this will be useful afterwards. Let me now move over to the combined resistor. The relation for the combined resistor and the current and voltages and voltage. In this case, there's only one voltage, which is the EMF. Right? The same voltage will appear across here. Okay, we are treating the internal resistance as part of this combined resistor in this example. So Ohm's law then tells us that E is equal to I times RC. So that's the overall voltage. That's the combined resistance. And that's all we have for this combined circuit. Now, we really want to find a formula for RC. We want to know how to calculate RC from the starting information, from the 3 ohm and the 6 ohm that are given. So I must somehow relate this equation to these equations. Now if you look at this equation, this one and this one, you see that they both contain E. So let me combine these two equations. Let me substitute this RC into the E. So, okay. So I'll get I times RC is equal to this, which is I R plus I little r. Okay, let me make it quite clear where this comes from. This comes from here. Okay, and this comes from there. Okay, so all I've done is I've substituted this into here. And then I get this. Okay, does this help? Right, notice that in this equation I have I of the current I as a common factor on both sides. So this means that I can divide both sides by I. If I do that, all the i's will cancel, and I'm left with exactly what I want. I'm left with RC, the combined resistor, is equal to combined resistance is equal to R plus small r, the sum of the two separate resistances. So I now have a way. So this is actually a way then to calculate the combined resistance from the separate resistors. So this is exactly what I need. Let me put this in square bracket. This is a useful formula that we can remember. And using this, I can now find a value for this combined resistance. All I need is to add the 3 and the 6 together. 3 plus 6, and the answer is 9 ohms. So if I put this 9 ohms in here, right, with the 1.5 volt EMF there, so 1.5 volt and 9 ohms, the current that I can now calculate would have the same value as this current. You can try that out.